So in the last video, we talked about binary trees and the binary search tree property. And in this video, I want to talk a little bit how we can analyze some operation like containsKey. And so we saw with the binary search tree property, we have to look at fewer nodes than in the without that invariant where we have to search every single one. And so let's try to talk about how we can quantify using our asymptotic analysis tools the runtimes of this containsKey operation. So what I have on this slide is I have two implementations of containsKey. One on the left is just for a plain old binary tree that does not have this binary search tree property. And what it does, let me clear that. What it does is it has your standard tree traversal code. It runs through the tree. If it ever finds the value, it returns true. Otherwise, in the recursive case, it makes a recursive call on the left tree, trying to find that value. And then it calls it on the right. So it kind of goes down both branches. Now, this kind of a callback to since it goes down both branches. Really, we're kind of in a situation a lot like our constant size input recursive pattern. Remember, we talked about these patterns that show up a lot in recursive code. And in this one, we're not like eliminating half the input each time. We're kind of just sticking with the same input. Now, it's not exactly constant size input since we're not looking at the values above us in the tree, but the pattern's really, really similar where you are kind of just recursing on approximately half the nodes remaining, right? For a second, let's just assume our tree is nice and balanced. Each time you're recursing on half the nodes, but you do that twice. And so that's about constant size input. And so if we use master theorem or any of that analysis, we kind of remembered that, that ended up being something like big theta event. We could be a bit more precise here, we will be, but this is like harkening back that you can get some intuition from seeing what pattern the recursive calls are in to figure out what the runtime might be, like an intuitive tool for this, not a rigorous one. And then for the containsKey binary search tree implementation, it's very, very similar, except down at the end. And here we only recurse down one of those paths. And so in this case, in kind of an ideal scenario, each time you eliminate half the tree, so we have this dividing by half behavior, our first recursive pattern we saw, which we saw was that theta of log n. And note, importantly, n in both of these contexts is the number of nodes in the whole tree entirely. Okay, so let's try to be a little bit more rigorous with this. So let's look at that containsKey on the binary search tree. It's pretty clear since I was hand waving a little bit that the runtime really depends on kind of a lot of factors here. It's not just the number of elements in the tree, but it's also kind of like what data you're looking for, what the tree actually looks like. So take a second and try to consider what are some interesting cases for us to consider when trying to come up with different runtime analyses for this binary search tree contains. What might be a best case value to look at, and what might be a worst case one? And what might the tree look like? So take a second to pause and kind of see what you think there. Okay? So for what I might have identified as maybe a best case, absolute best case, you're looking for the key at the top of the tree. So say in this specific tree, you're looking for key 9, you can just return immediately. You don't have to do any traversal down the tree. And so in that context, in that case, you remember case analysis, we come up with a case, we're searching for the node at the top. Then no matter how many nodes are in the tree, that's going to be a theta of 1 operation. I would argue something like the worst case is searching for a key that's not there. So say for like the key is 100. You have to go down the whole tree, and to find out that there's nothing there, you have to go all the way down from 9 to 10 to 30 to nothing to find that the 100's not there. And so in this case, I would argue it's closer to that theta log n behavior. Now, that is under a couple assumptions. So let's talk about that real quick. This is assuming that the recurrence you can come up with is something like this, where you have T of n is this T of n over 2, where you're dividing the total number of nodes in half each time, plus some constant work, and then the base case is constant work. You can plug these constants into master theorem, and you get log n for your output. But there's been a couple things here. Is it possible for us to do something a little bit worse than big theta of log n? So let's consider what sources of variation affect the runtime of the kind of the whole operation. So I'd argue that there's three main sources of variation: the number of elements in the tree n, the position of the key that you're searching for in the tree, and the arrangement of the tree itself. Now, as a reminder, when we're thinking about case analysis, we are not allowed to fix the number of elements in the tree for a particular case, right? So even though this is a source of variation, it changes the runtime overall. When we're thinking about cases, we want to fix something other than the input size, because the input size needs to be used like a free variable of some sort, so your runtime function's defined for any size. So then I would argue for the cases you're thinking of, it's going to be the position of the key and the arrangement of the nodes. Now, can we make this runtime, theta log n, when we're searching for a key that's not in the tree, worse than theta log n if we change the tree around? And I would argue that we can. I'm going to show you this horrible picture, this terrifying image of a binary search tree that has a worst case runtime worse than log n. This picture I've shown you right here is what we call a degenerate tree. It's technically a binary tree. It's also technically a binary search tree because it's sorted in the binary search tree property. 0 is at the top, and then 1, and then 2, and then 3, all the way down. Okay? Now, imagine if this tree had n nodes in it, right? Because we can't fix n. So if there's n nodes in this tree, well, what is our recurrence going to be? Well, on each iteration, we're only in the worst, in this arrangement, assuming, let's say we're looking for a key that's at the bottom, because if we're looking at a key at the top, the arrangement doesn't matter. If the position of the key you're looking for is at the top of the tree, it doesn't matter if you're in this degenerate case tree or any other tree, you're just going to return right away. But if the key you're looking for is maybe not in the tree, and this tree is in this degenerate format, well, then your recurrence is going to look something like, well, on each recursive call, you decrease the input size by 1 because you just eliminated the node that you're currently looking at. Then you have some constant work at the bottom. Now here, you can't apply master theorem because it's not in this division format. But you can use the tree method and do a little bit of math, and you show that this would end up being big theta of n. You can also kind of intuit why that would be, because each time you're kind of just going down the tree until you run out of spaces. So in the absolute worst case, this tree can yield a search time that's big theta of n, not log n. And that should cause a little bit of concern here, because if you remember back from 143, we kind of promised you that tree maps are efficient. They're always log n operations. But this is a binary search tree that is valid, but results in theta of n runtime, not log of n. So considering our two different extremes here, kind of this very perfectly balanced complete tree where every node has 2 children up into the leaf nodes, this is a perfectly balanced tree. Everything is right in the world. And in this worst case, we have this degenerate tree where all of the nodes are just in the right subtree. You can also have a degenerate tree going to the left, but it's really kind of this one unidirectional tree. Now, one of the things that if you think about this, it actually is really just like a fancy linked list, right? Where everything is just going from start to end. Now, when we're trying to think about how to do better here, I argue that the key difference between these two trees is the height of the tree, right? Both of these trees have n nodes in total, but the perfectly balanced tree has a smaller height than the degenerate tree. So my argument here is that what ends up determining the runtime of your binary search is the height of the tree overall. The height both describes that degenerate case and that perfect case. So in the worst case, when we're trying to find a key that's not in our tree, then the runtime is going to be proportional to the height of the tree. So our trick that we're going to introduce kind of in the next lecture, how we can make sure that this stays efficient, is some mechanism to make sure that the height of the tree doesn't get too large. We make sure it's a proper height. So how do we come up with a limit to make sure that our tree is in a proper structure? Well, that probably is going to be a hint that we're going to add another invariant. Add a new invariant to our data structure to make sure that its height doesn't get too big. Now, I'm not going to go through completely how we're going to implement this invariant or what the answer is going to be. But I do want to spend a little bit of time talking about what would an invariant for this, what might it look like? What might we want from an invariant here to make sure our tree stays short? It doesn't have too much of a height. So here's my example of an invariant I might want here. What if I added an invariant that the height of the tree must not exceed big theta of log n? What I mean by that is we said that we want that log n runtime. So let's just make this invariant in the tree that the only trees we're allowed to work on are trees that have height that's log n tall. Okay? That's a very useful invariant. This is exactly what we want, and it would be entirely true, entirely useful if we could assume it's true on entry, right? So like when we call it containsKey, you can assume, oh, I know the height's going to be log n because this is my invariant. And so we have this not too bad worst case runtime. But think about when you're trying to do something like insert a node to a binary search tree. When you're inserting a value, you kind of go down the tree to try to find its right spot, and then you put it kind of in the right spot, in the right place from that. But it's not clear at all how you implement something like insertion or removing to make sure that that invariant is true on exit. For example, if every time you insert the node, do you have to rebuild the tree from scratch to make sure it's nice and balanced? If that were the case, that would be a really slow implementation of insertion. So what we're going to actually see here is that there's a bit of an art to coming up with invariants. Because remember, invariants are tools for us to use to help us simplify our code, to help us make sure we know it works. This invariant, I'd argue, is too broad. It's exactly what we want in theory. We want to constrain the height, but it doesn't give us any hints on how we can implement our code to do this. And so what I would argue is that we want an invariant that is a bit more prescriptive, that tells us this is exactly how you meet this invariant such that we have this kind of bounded height. So that's one of the things that we're going to start seeing in Wednesday's lecture, is coming up with a new invariant that does not really say anything necessarily about the height being log n, but is very easy to maintain. And we'll show that that kind of new invariant actually guarantees us this log n height. Okay? And that's going to be the focus of Wednesday's class on these things called AVL trees.